Hello, class, and welcome back. Let's continue our discussion on Chapter 6, which is columns. We'll look at some of the design considerations of it. Uh, just a quick review of what we've looked at is our design factor as it applies to our critical buckling load, our allowable load, and our long column analysis. All right, so moving forward, we'll look at section 6-6, which is our slenderness transition slenderness ratio. I have it backwards. Transition slenderness ratio. Right. So if we pull up equation 6-6, right, that was our critical buckling load is equal to pi squared modulus elasticity times our cross-sectional area divided by our slenderness ratio quantity squared. Right. This equation 6-6. Something I failed to mention last time is we call this our Euler or Euler, however you want to pronounce it. I believe the correct one is Euler. We call this our Euler formula for long columns. And now if we take this Euler formula for long columns and we rearrange it slightly, and we move the cross-sectional area to the left-hand side of the equation, like thus, we have pi squared modulus elasticity divided by our slenderness ratio quantity squared, and this is equation 6-7 in our textbook. Right? So this allows us to make a quick plot. Right? And if we notice on the left-hand side of the equation, this is actually a stress. Right? So I'll use sigma as a stress, and we could denote that with a subscript critical there. Not necessary and not done in our textbook, but something I'm going to take the liberty to do myself and hopefully get this pen to work. There we go. And we make a plot using this. And we say that our slenderness ratio is on the abscissa or the x-axis, where it's KL over our radius of gyration, where K is our end fixity constant, L is the length of our column, and R is the radius of gyration, and the ordinate, or the y-axis, is our critical buckling load over the cross-sectional area. For various materials, we can create a plot that can look something like this. Now these are arbitrary lines. I'll just do it nice or do it twice, right? These are arbitrary lines. There's no numbers or no actual data associated with this one I'm drawing, right? There's actual data and actual graphs out there. But I'll just say that maybe this is aluminum and maybe this is steel. Right? If we look at this formula, as our slenderness ratio approaches 0, our critical buckling load divided by our cross-sectional area will move to infinity, right? So if we have a column with a fixed cross-sectional area, our critical buckling load cannot go to infinity. That doesn't make physical sense in our realistic world. Maybe in another dimension or something, but not in ours. Right? So what we need to do is define a point at which the Euler formula for long columns no longer applies, and we have to move on to another formula, which is called the J.B. Johnson formula for short columns, and I'll write that out here in a little bit. But excuse me. What we're going to do is we're going to define a transition point, right, or a transition zone. And this is actually going to be a point on this particular graph or this particular formula. And what we're going to do is we're going to say that that's equal to the yield strength of the material divided by 2. Right? So again, the yield strength is a stress. So if we set that equal to our critical buckling load over our cross-sectional area, which is also equal to pi squared times the modulus of elasticity divided by our slenderness ratio, quantity squared. We can actually denote, I'll use a different color, perhaps red. Right? We can actually denote our slenderness ratio as a different term. Right? We'll say it's our slenderness ratio in transition. So slenderness ratio with a subscript capital T here, and I'll make it a quantity squared just for consistency. So if we rearrange our formula to solve for our slenderness ratio in transition, we can say that it's equal to 2 times pi squared times the modulus of elasticity divided by our yield strength, quantity square root. And this is equation 6-8 in our textbook. Now another term for our slenderness ratio in transition is our column constant, denoted by C subscript C here. So we have our column constant and our slenderness, let me write that R correctly, slenderness ratio transition. Right? So if we go back up to this graph, and maybe that point for steel is right here, and maybe that point for aluminum is right here. Again, it's based on the material properties, the modulus of elasticity, like so. And we draw a vertical line. We don't draw a vertical line. There it goes. We draw a vertical line at that point. Now, if I change colors to red, we can highlight the impossible portions. Well, maybe not impossible, but the incorrect portions. Well, there we go. Of this graph here. Right? And we can say that those don't really necessarily apply because our column is now considered a short column. All right? So what I'm going to do is I'm going to change colors again to a blue color, and I'm going to draw a, oh, that does not help. I'm going to draw a parabolic dashed line in theory. Something like this. Now again, these are not necessarily exactly accurate based on aluminum and steel, so bear with me on that. Well, where these intersect with the abscissa, forgive me, the ordinate, the y-axis, is at the yield strength of the material. Right? So this point right here, where the dot is, this point right here is our column constant, or our slenderness ratio in transition, based on our material modulus elasticity and yield strength. Right? So with that in mind, what we're going to do is we're going to move on to section 6-7 and draw the equation for short columns. So 6-7 is our J.B. Johnson formula. All right, for short column analysis. Right? So this book does not go into the derivation, but it has references that will allow you to research the derivation of this formula on your own. If you are so inclined, we can look at it together. But we will take this formula as it's written as useful and valid. Excuse me. So what it says is that our critical buckling load, P critical, is equal to the cross-sectional area times the yield strength times quantity, 1, minus yield strength times our slenderness ratio squared divided by 4 pi squared times the modulus of elasticity and quantity. And this is equation 6-9 in our textbook. Right? So just a quick recap is that we look at our slenderness ratio. So let's do it like this. We'll say short column, and we'll say long column. And we say that our slenderness ratio, which is equal to our end fixity constant times the length of our column divided by our radius of gyration, is less than our slenderness ratio in transition, or our column constant. Then we use our P critical is equal to A SY 1 minus SY SR squared over 4 pi squared E. Right? Now, if we say that our slenderness ratio, which is equal to our end fixity constant times our length over our radius of gyration, is greater than our slenderness ratio in transition, or our column constant, then we're going to use our P critical is equal to pi squared modulus elasticity times cross-sectional area divided by our slenderness ratio quantity squared. So just a quick recap there. All right, so moving on from here, we are not going to cover 6-8 or 6-9 in the lecture. I recommend that you read them. They are fairly short and fairly useful, but there's nothing that will be necessarily drawn out of them for the purposes of an exam. So moving on to section 6-10, design of columns. So in a design situation, generally what you as the designer or the design engineer will have is an expected load, right? So we're going to say that we have an actual load, P. Let me just write that so it's legible. P, actual load. And we will also have a length of column or part or shaft or whatever kind of part you're designing. You'll have the actual length. So what the designer is going to have to specify, or you as the design engineer are going to have to specify, are several conditions. One being the end fixity conditions. Okay, let's try that again. End fixity. 2, the general cross-sectional shape. 3, the column or part material. 4, the design factor. Oops, there it goes. Design factor. Again, that's N, also called a safety factor, depending on who you ask. And 5, the final dimensions of your column. So what I'll say is that we're given something like this, right? We're given, a load and a length of our column, and we want to specify the end fixity conditions, the general shape of cross-section, the column or part material, the design factor, and the final dimensions of the column. So what we'll do is we'll consider our long column or our short column information. And you want to put all of the equations that we've looked at all together. So something that we can do is we can take equation 6-4 and we can rewrite it, right? Again, equation 6, well, I won't go all the way up there. I'll just rewrite it here in just a second. We can say that our equation 6-4 is our critical buckling load is equal to pi squared times our modulus elasticity, times our area moment of inertia I, over our length equivalent squared. Right? So what we can do is we can rewrite that if we're looking at a long column, again based on our slenderness ratio compared to our column constant. And we can say that our I is now equal to our critical buckling load times KL quantity squared, where this is our equivalent length, right? Recall equivalent length is equal to KL, right? K being our end fixity constant, divided by pi squared modulus elasticity. Now, if we recall that our allowable load is equal to our critical load divided by our design factor n, we can replace our critical load here with n times our allowable load times KL quantity squared divided by pi squared modulus elasticity. And this is equation 6-10 in our text. All right. So now what we can do is we can say that we know all of these conditions on the right-hand side. So I'll use maybe a blue. Known, given, or we specify them ourselves. Now we can not change colors. Try to change colors to maybe a green. Now we can solve or choose a certain type of cross-sectional area or a certain type of beam design that will result in a good or allowable or satisfactory area moment of inertia. All right, so if I continue with the example in the book and we say that example, very brief example, we choose a solid circular cross-section, we can say that I is equal to pi d to the fourth over 64 from our appendix A. Right? So now we can set that equal to our equation up here from 6-10. We can say pi d to the fourth over 64 is equal to n allowable load times KL quantity squared over pi squared times our modulus elasticity. We can solve and say that our suitable diameter is now 64 times n times our allowable load times our n fixity constant times our column length quantity squared over pi cubed times our modulus elasticity. Just forgot the equal sign there. This quantity to the 1/4, right? So this is just an example of choosing a solid circular cross-section. If you choose a different sort of cross-section, you can plug in the appropriate area moment of inertia and look at it and see what sort of dimensions and area and all of the appropriate dimensions are. Sorry, I said dimensions twice there. So that's for a long column here. Now, if we take the same sort of approach and we look at our equation for a short column, and we take something that says P critical is equal to area times our yield stress times quantity 1 minus our yield stress times our slenderness ratio quantity squared over 4 pi squared times our modulus elasticity here. And we do the same thing with choosing a solid circular cross-sectional area. for example. Not necessarily the case for all parts and all sorts of designs, but it's a good example, right? We can replace some of these values, or not some of these values, but these appropriate values, and we can say that area is equal to pi d squared over 4, right, from Appendix A, and we can say that our P critical is also equal to n times our P allowable, right? And we can replace all of these terms, and we say NPA is equal to pi d squared over 4 times our yield stress times 1 minus our yield stress times KL, quantity squared. Again, that's our slenderness ratio, plugged into our equation up here, divided by 4 pi squared times our modulus elasticity times d over 4 quantity squared, right? Again, that's from our slenderness ratio, okay? So I'll write that up here as soon as my pen starts working again. There it goes. Right, where our slenderness ratio is equal to KL over radius of gyration, right? In this case, our radius of gyration is equal to d over 4 for a circular cross section, right there. So that then plugs in down here. And we have this equation, and then we can solve this for our d factor, or excuse me, our d as diameter, and we can say 4 times our design factor times our allowable load over pi times our yield stress plus 4 times our yield stress times our n fixity condition times our column length, quantity squared, over pi squared E quantity to the 1/2. Again, this is an example for a solid circular cross-section. Now, if you wanted to look at something, some other sort of design, you'd have to do a little bit of math and a little bit of algebra to look at the design of the area, a certain base, a certain height, a certain area moment of inertia. Some of the other popular or commonly chosen designs include our flanged or our I-beams with our webbing and our flanges. We have hollow tubes. We have, that's a tube, right? We have hollow rectangular columns. These are some common, this common column cross sections that are often used in design. Now, the rest of the chapter, 6-11, 6-12, and that's it. We're not going to cover those in this course. They're good reference material and good information for you for applying these sorts of design factors in the real world or in odd or unusual circumstances, but we won't be covering them for the purposes of this course. So that concludes our lecture on Chapter 6, Columns. Your homework will be assigned shortly, and I'll upload these notes so that hopefully you can print them and then follow along with the lecture and make any additional notes that you would like to.